Like in the last class, we started benzene. But today I just want to go through with some past paper questions. Right? I didn't share the paper because I wanted to do it like in the live session. So today we'll do some questions from the chapters which we have covered, like electrochemistry and transition metals. And then we'll continue with the benzene. All right. So for each question, like what is the electronic configuration of chromium atom? This is simple, just ignore it. Which ion shows the typical properties of transition metals by forming colored complexes? Yes.
So just give me a minute. Let me just connect my charger. Right. Just give me a minute.
Okay.
It's very low.
Okay. So which ion should the which ion shows the typical properties of transition metal by forming colored complexes? Yes, what could be the answer? A, Cu plus, B, nickel ion, C, scandium 3 plus, or D, zinc 2 plus ion?
Is it zinc? Sure.
Typical property of metals, transition metals by forming colored complexes. Zinc, like we have discussed, zinc is not a transition element because it's D subshell when it is in Zn2 plus form. So its D subshell would be fully filled. Zinc has 30 electrons, as you can see from, like if we look from here. So the atomic number of zinc is 30. So once it loses 2 electrons, it would be 1s2, 2s2, 2p6, 10, then 3s2, 3p6, right? And after 3p6, it will be 4s2 and 3d10. So this is the electron configuration of zinc. But once it loses 2 electrons, then so Zn2 plus has this configuration in which the D subshell is fully filled. So this is not a transition element, and that's why the compound of transition of zinc are colorless, like zinc chloride or zinc nitrate. They're all colorless. So zinc is not the answer. Is it clear?
Yes, sir.
And likewise, scandium is also not an answer because in scandium, again, the same thing happens. Scandium has an electron configuration of 21. So once it loses 3 electrons, this will be 1s2, 2s2, 2p6, 3s2, 3p6, 18, then 4s2, and 3d1. So losing 3 electrons, that means 4s will be lost, 3d will be lost. So it has 0 electrons in 3d. That's why scandium plus 3 ion or scandium is also not a transition element. Copper, although it forms colored complex, but in +1 state, copper has an oxidation number of 29. So if you write the electron configuration of copper, 1s2, 2s2, 2p6, 3s2, 3p6, then 4s2, and 3d9. But we know one of the electrons from 4s into 3d. Remember this thing?
Yeah.
So copper has this exception that one of its electrons from 4s will move into 3d. So this will be the electron configuration of copper. So once it loses 1 electron, its 3d is fully filled. So Cu plus will also not act as a transition element. So it will not give complex, colored complex. But if it is Cu plus 2, then it could be an answer. But here they have given us Cu plus. So the only option left is nickel Ni2 plus ion. And nickel ion will give colored complexes. You can write the configuration of nickel ion. Nickel has an atomic number of 28, right? So that means after 4s, it has 8 electrons. So if the 4s electrons are lost, still it has 8 electrons. So it is half filled. So that's why nickel can give us colored complexes. Nickel would be the answer. Is it clear? Okay, the next one is the formula of a chromium compound is, they have given us the formula of this complex, right? The molar mass of the compound is, this is the molar mass of compound. What is the percentage by mass of chlorine in the complex ion? What is the percentage by mass of chlorine in the complex ion? We have to tell the percentage by mass of chlorine in the complex ion. Can you do it?
Yeah, I will. Yes. Yeah.
Okay.
Try.
All right.
So we will subtract the molar mass of the chlorine ion with the molar mass of the compound, right? First, and then
Yes.
multiply two chlorine atoms and find the
Mhm.
percentage. Okay.
Yes.
This is 36.4.
It is 36.4. So they have asked
Yes.
us the percentage by mass of chlorine in the complex ion. So that means we'll subtract this Cl from the total mass, right? And then the percentage by mass, because in complex there are two chlorine. So we'll multiply the Ar of chlorine by 2 and the Mr of complex ion multiply by 100. So the answer would be 36.4, which is C, right?
Yes.
All right. Now the next question is the reaction between peroxo disulfate ion and iodide ions is shown. Right? They've given us this reaction between peroxide disulfate ion and iodide ion. If you remember, we have discussed it in homogeneous catalysis, right? The
Yeah.
reaction has a high activation energy, but it is catalyzed by iron 2 ions. What is the best explanation for the high activation energy of this reaction? Yes, why the activation energy is high for this reaction? The peroxo disulfate ion is a weak oxidizing agent. Is this the reason? The iodide ion is a weak reducing agent. Peroxo disulfate ion and iodide ions are both negatively charged, or the reaction involved three reactant ions. Yes, what is the reason? Jivita, what could be the reason? What is the best explanation for the high activation energy of this reaction?
Um, Let it be the first one.
No, actually, they both are very good oxidizing and reducing agents, but because there is negative charge on both of them, so they will repel each other. If you remember, we've discussed this as well, that because of their negative charges, they'll repel each other. So we'll have to put a lot of energy to make them react. And that's why they have very high activation energy. So peroxodisulfate and iodide are both negatively charged. And due to that charge, they'll repel each other. Is it clear?
Yes.
Okay. So they both are negatively charged. So answer is C. Which property of iron 2 ions? Which property of iron 2 ions? It is related to the same uh, concept. Like we are using iron 2 ions as a catalyst. So which property of iron 2 ions enable them to function as a catalyst for this reaction? First of all, what type of catalysis would it be? We're using iron as a catalyst, Fe2 plus ion as a catalyst. So what type of catalysis is this? Is it a homogeneous catalysis or heterogeneous?
Homogeneous.
Yes, it is homogeneous. So now they're asking that which property of iron 2 ion enables them to function as a catalyst for this reaction? Iron 2 ions can be easily reduced to metallic iron. Is this the reason? Iron 2 ions effectively absorb the reactants, or iron 2 ions can be easily oxidized and then reduced, or iron 2 ions can be easily reduced and then oxidized.
It will be easily oxidized and then reduced, right?
It will be easily oxidized and then reduced. So why are you saying this? Yes, what is the reason? जी बेटा.
Yeah, I'm sorry, sir.
What's the reason for this?
So it will be as far as I understood, so the oxidation state.
Mhm. Like because it is homogeneous catalysis, so we know that there will be some change in the oxidation number of the catalyst. Catalyst itself will get involved in the reaction, and
Yes.
Fe2 plus ion, like we discussed it in theory, that Fe2 plus ion will itself get oxidized during the process. So Fe2 plus will oxidize. It will act as a reducing agent. So it will react with the particle which is getting reduced in this reaction. So which particle is getting reduced? Is it iodide ion? Iodide is changing from -1 to 0. So this is getting oxidized. So obviously Fe2 plus cannot react with iodide ion. So it will react with peroxodisulfate ion. You getting me?
Yeah, okay.
Right. So this will react with peroxodisulfate ion, S2O8, 2 minus. In the process, peroxodisulfate ion will get reduced into sulfate ion, and Fe2 plus will get oxidized into Fe3 plus. And then this Fe3 plus will react with iodide ion, and this time iodide will be oxidized into iodine, and Fe3 plus will reduce back into Fe2 plus. So we get a catalyst back. So we can say that it can be easily oxidized and then reduced. That's why it can be act as a catalyst. But if, let's suppose they ask you about Fe3 plus ion, let's say if they're using Fe3 plus as a catalyst, because this can be used as a catalyst as well. So then the answer would be it can be easily reduced and then oxidized, because Fe3 plus will initially react with iodide ion and then it will react with peroxodisulfate ion. Is it clear?
Yes, okay.
All right. Chromium hydroxide, this is the formula, is amphoteric. This means that chromium 3 hydroxide dissolves in, yes, what is an
Amphoteric means
amphoteric
it
substance?
can act as both acid and a base.
Acid and a base. So that means it can be dissolved in strong acid and strong
Strong
alkali,
acid and strong alkali.
right?
Yes. Yeah.
Okay, this is organic section. All right, which pair of equation shows the most likely mechanism for vanadium 5 oxide acting as a catalyst in the contact process? They've given us four equations. Which pair of equation shows the most likely mechanism for V2O5 acting as a catalyst in the contact process?
So here the vanadium is first reduced and then oxidized, right? Or is it the other way?
First of all, you have to decide vanadium will react with like V2O5, it will react with oxygen or it will react with sulfur dioxide.
Will we react with sulfur dioxide?
Sulfur dioxide. So that means it is either option B or option D, right? So you have to decide between option B and D. And now in B, if you look into the equation B, we can see that sulfur dioxide is getting oxidized into sulfur trioxide. Yes, this is correct. And V2O5 is changing its oxidation state from +5 to +1, which is not the oxidation state of vanadium. Vanadium, if you can remember, we have discussed the oxidation states of vanadium. It is +2, +3, +4, and +5. So vanadium do not goes into +1 oxidation state. So that means this is not the answer. So if you look at option B, V2O5 is converting into V2O4, in which the oxidation number of vanadium is +4. So this gets reduced from +5 to +4. Sulfur dioxide oxidizes to sulfur trioxide. Later on, V2O4 reacts with oxygen and converts back into V2O5. So option D would be the correct answer. Is it clear?
Yeah.
Right. Okay, then next one is the formation of carbon dioxide from the reaction between manganate 7 ions and ethane dioate ion is autocatalyzed by manganese 2 ions. Now, you know what is autocatalysis? Yes, any idea about autocatalysis?
Um,
Give it down.
so it's not sure, sir.
Like autocatalysis, as the term suggests, it is like when we have a reactant or a product start acting as a catalyst. So we say that reaction is catalyzing itself, and most of the time it is one of the product which start catalyzing the reaction. So if a product start catalyzing a reaction, it is called autocatalysis. So if a reaction is being catalyzed by one of its own product, then we say that it is autocatalysis. Reaction is catalyzing itself. All right. So in this question, they're saying that the formation of CO2 from the reaction between manganate ions and ethane diiodine, here we're getting carbon dioxide by reaction of manganate ion with ethane diiodine is auto-catalyzed by manganese 2 ion. So this Mn2 plus will catalyze the reaction. So which graph for the complete reaction shows the auto-catalysis of this reaction by the manganese 2 ions? Yes, so which graph would be the correct graph for the auto-catalysis for the reaction? Like we're getting volume of CO2, carbon dioxide on the y-axis, and time on the x-axis. So it's volume time graph. So obviously, the volume of CO2 will increase, and this is auto-catalysis. So which graph could represent this reaction? So and normally it would be something like this for a normal reaction, where
Yeah.
volume of carbon dioxide will form, and ultimately, uh, like it goes constant, it stops forming. But when we talk about an autocatalytic reaction, so the graph would be something like this. Because initially, the rate of this reaction, the slope of this reaction represent the rate, right? The slope
Yeah.
of volume time graph is the rate of reaction. So initially, the rate of the reaction would be slow because in a start, there is no Mn2 plus or very little Mn2 plus. So it starts with a low slope, you can say with a slow rate. But as soon as the Mn2 plus will start forming, the graph will getting steeper and more steeper, and ultimately it goes constant. So for an autocatalytic reaction, the graph would be always it would be like this. Like initially it would be slow and then takes speed. Then it becomes faster. The graph gets steeper. So this will be the answer. Is it clear?
Yes, sir. Okay.
Okay. Now the theory part. Okay, so this question is about electrochemical cells. Describe how you would carry out an experiment, how you would carry out an experiment to determine how you would carry out an experiment to determine the standard electrode potential of the electrode system shown. We have this electrode system, cobalt in contact with cobalt 2 plus ion. So you have to determine the electrode potential. So describe how you would carry out an experiment to determine the standard electrode potential of the electrode system shown, right? Assume that you have access to the equipment and chemicals that you need, describing their use in your answer. You may include a labeled diagram. So it's a 6-marker question. So you know how to answer this one?
So we'll draw a diagram, right?
Yes, you'll draw a diagram.
The hydrogen electrode and then the cobalt
Obviously, we'll
on
draw
the
the
other side.
hydrogen electrode and the cobalt in contact with cobalt ions, right? We'll have
Yeah.
this diagram in which we have a platinum electrode, the platinum wire, and hydrogen is passing through this electrode. Right? And from this point, we are passing hydrogen gas. This is the standard hydrogen electrode. And then we have the other electrode, the other half cell in which we have cobalt being used as an electrode. And it is dipped in a solution of cobalt 2 ions, 1 molar. Right? So this is cobalt, and they are connected to each other through a voltmeter, which will give us a reading, and a salt bridge. So this is a basic diagram, right? So first you'll describe that we'll use hydrogen H plus ion as standard hydrogen electrode, right? And the conditions will be 1 mole per dm cube, and gas passes at 1 atm, temperature 25 degrees centigrade. These will be the conditions. And cobalt solution, cobalt electrode dipped in 1 mole per dm cube cobalt ion solution. Both the half cells are connected by both the half cells are connected by salt bridge. Salt bridge. If you want to give the details of salt bridge, you can provide that it's let's say filter paper soaked in an aqueous solution of sodium nitrate or potassium nitrate. So filter paper soaked in aqueous, let's say sodium nitrate, right? A high resistance voltmeter, both the all right, we haven't mentioned the platinum electrode in hydrogen half cell. So both the electrodes are connected by a high resistance voltmeter. Right, we'll connect them to a high resistance voltmeter, and then the EMF or voltage we get on voltmeter will be the electrode potential of CO2 plus CO half cell, as standard hydrogen electrode has a zero electrode potential. Is it clear? Right. So this would be the answer. Now you can write it in your own words. I just write the major points, right?
Okay, sir.
So this is all you have to discuss in this question. The next question is acidified potassium dichromate is an oxidizing agent. Acidified potassium dichromate is an oxidizing agent. The acid commonly used is sulfuric acid. Explain using reference to the electrode potentials shown why concentrated hydrochloric acid should not be used to acidify potassium dichromate. Yes, they're saying that potassium dichromate is an oxidizing agent, and we use sulfuric acid to acidify this oxidizing agent. But why we cannot use concentrated hydrochloric acid? Using reference to the electrode potentials, we have to explain why we cannot use hydrochloric acid to acidify potassium dichromate.
So we can take the E cell value, right? The 1.33 minus 1.36. Then we get minus 0.03 volts. Can you hear, sir?
Yes, so the output disconnected.
Okay.
Let me just share the screen. Yes, like you read the question.
Yeah.
So can you suggest what could be the answer? Just give me a minute, but I just read the question. I'll be back just in a minute. जी बेटा, every
Yes, sir.
like your answer for this question?
Yes, sir.
Yes.
Okay, so,
So what
so
could
I
be the answer?
found the E cell value first, and it's like minus 0.03
Mhm.
volts. And I wrote since
Minus
the value
0.03 volts. And how you get this answer?
it's 1.33 minus 1.36, like reduction.
All right.
Okay, and then
Okay.
if since the value is very small, um, So
Okay,
using
it's
the
very small.
concentrated
So
acid, it will reduce the chlorine electrode potential. Therefore, the oxidation of the chloride to chlorine will not happen. It's not feasible.
all right, like if we perform the reaction in standard conditions and we are considering potassium oxidizing agent, that means it will get reduced. So it will, if it will get reduced, so this potential and this will be the oxidation potential. And from here, if we calculate 3 minus 1.36, that would be minus 0.03. So under standard conditions, it would be like very slightly feasible. All right, this is what we want to say.
Yeah,
And
yes.
if we start using concentrated acid, on using the concentrated acid, the concentration of chloride ion will increase. Right? If concentrated hydrochloric acid is used, the concentration of chloride ions will increase. The concentration of chloride ions will increase. The equilibrium shifts backward. And we say that the E electrode of Cl minus Cl2, because if the equilibrium shift backward, that means this will get less positive or more positive.
Less positive.
Less positive, right? Because more oxidation occurs, it will start losing electron. Likewise, if we use concentrated acid, the concentration of H plus ion will also increase, and this equilibrium will shift forward. So we can say that equation 1 shifts forward, and the E electrode gets more positive. So this can start acting as an oxidizing agent if we use a concentrated acid, right? So if we use a concentrated acid, then potassium dichromate can act as an oxidizing agent against hydrochloric acid. But the problem is we start getting chlorine in this reaction, which is a highly toxic gas. So chlorine gas will produce, which is a highly toxic gas. And that's why this would be not feasible to use concentrate. At normal conditions, this cannot use because it is marginally feasible. And at high concentration, again, this is not feasible because we are getting a very toxic gas in this reaction. So that's why we do not use hydrochloric acid to acidify potassium bichromate. All right.
Right.
The cell diagram for an electrochemical cell is shown. Write the reduction half equation. Reduction half equation for this electrochemical cell. State symbols are not required. The reduction half equation would be the one on the right side, because this one, the first one will be the oxidation one, and this is the reduction one. This one is the reduction one. So dioxovanadium VO2 plus reacting with 2H plus ion,
2H plus.
because it is
Electron.
2H plus ion. This will give us VO2 plus H2O, right? And on this side, we have plus 2 charge. And on the reactant side, we have plus 1, plus 2, plus 3. So to balance, we'll add an electron here. All right?
Yes.
So this is how you'll write the equation. And now, the direct methanol fuel cell use methanol and oxygen to generate electricity. When the cell operates, the methanol reacts with water at one electrode to produce. When the cell operates, the methanol methanol reacts with water at one electrode to produce carbon dioxide and hydrogen ions. Right, at one electrode, methanol reacts with water to produce carbon dioxide and hydrogen ions. At the other electrode, oxygen reacts with hydrogen ions to form water. So these are the two half equations. Write the oxidation half equation for this fuel cell. So obviously, methanol will get oxidized. So the methanol half equation is the oxidation one. So we'll write the oxidation half equation. It will be methanol reacting with water, converts into carbon dioxide, it get oxidized, and hydrogen
Yes.
ions, H plus ions.
Yes.
Now we'll balance it. So we have 3 plus 1, 4, plus 2, 6, right? 6 hydrogen ions, 6 H plus. And because it has a 6 H plus, so we have to add 6 electrons to balance it. So the equation. Is it clear?
Yes, sir. Clear.
This clear? Fuel
Yes, that's
cell?
clear. Yeah.
Okay. State symbols are not required. So the overall equation would be combustion of methanol. We can just simply write, or you can just add the both equations, but we know it is combustion of methanol. So we can just simply write the equation for the combustion of methanol. It would be CH3OH reacting with oxygen. This gives carbon dioxide plus water. This will be the equation, combustion equation. So we'll balance the equation, balance on both sides. So we have 4 hydrogen atoms. It would be 2 oxygen. So that means this would be 3 upon 2. All right.
Yeah.
The reduction half cell in the DMFC has a standard electrode potential of this. This is the reduction potential of the reduction half cell. When the solution concentration changes, the electrode potential changes so that E is equals to 1.20. The relationship between these values is given by the equation. They're giving you this modified form of the Ernst equation, where X is the concentration of the solution in moles per dm³. Calculate the value of X in the non-standard half cell.
Yeah.
Give it as.
Yes, I calculating.
We have this. Okay, we have the equation E is equals to E naught 4.277 into 10 power minus 3 natural log of X. So you have both E and E naught value, you just have to calculate the X.
So I got the lnx values.
Sorry?
I got the lnx value, but
Okay.
what do we do after that?
You'll take the inverse of natural log.
That's okay.
Like we have the E value, E is 1.20, E naught is 1.23 plus 4.277 into 10 power minus 3 natural log of x. So this is equals to 1.20 minus 1.23. 1.20 minus 1.23 is equals to minus 0.03 minus 0.03 is equals to 4.277 into 10 power minus 3 natural log of x. And then this value becomes 0.03 divided by 4.277 into 10 power minus 3. No, this is minus 7.01. The natural log of x is equals to minus 7.014. This is the answer.
Yes, sir.
7.014. And then we'll take natural log of x. When it goes on the right side, it goes log inverse, natural log inverse. So this would be e to the power exponent, e exponent. The natural log ln x is equals to, if it goes on the other side, according to mathematics, the inverse of natural log is e power x. Euler's constant. So we can just simply write e to the power minus 7.014. And on the calculator, you just shift log inverse, natural log, shift ln, and the value is minus 7.014. So this would be the answer, 8.99 into 10 power minus 4. You get it?
Yes, 8.99.
8.99 into 10 power minus 4. So this would be, so you can write either this or you can write inverse of natural of ln. So this will be the answer. All right.
All right.
Okay. Now the next question is this question is about the colored transition metal complex ions. Colored transition metal complex ions. The complex FeH2O6 2 plus complex ion is green, and FeH2O6 3 plus complex ion is yellow. Explain why the FeH2O6 2 plus complex ion is colored. So we have to explain the color theory, why the hexa-aqua Fe2 plus ion is colored. So the reason is when the transition metal it get connected to the ligands, the D subshell it gets split into two different energy levels. Once the Fe2 plus ion make complex with H2O, the ligands repel the electrons in 3D subshell, due to which D splitting occurs, right? First point, D splitting occurs, and the energy gap between D orbitals lies in visible range This kind of DD splitting which we have discussed, the xy, the xy, the yz, the zx, the x square minus y square, and the z square. So this DD splitting occurs, and the difference lies in visible range. So, like one of the electron from the lower energy level, let's say if we have this electron here, one of the electron from the lower energy level will absorb energy and it jumps into the higher energy level. Rest of the energy is transmitted, and that transmitted light is the complementary color. This will give the color to the complex. So an electron from the lower energy level, electron from lower energy level absorbs a certain frequency and rest of light is transmitted. And this gives the color to the complex. This transmitted light gives the complementary color. Is it clear?
So we're not supposed to include the photons thing, the electrons in low energy orbital, they absorb photons and then.
Yes, we discussed that.
Okay.
Like in this point, electron from the lower energy level absorbs certain frequency. You can say a photon of certain frequency, right? It's the same thing. Is it clear? Okay, it absorbs a certain radiation, or you can say it absorbs certain amount of photons, and it jumps into the higher energy level. Rest of the energy will be transmitted, and that transmitted light will be the reason for the color. Is it clear?
Yes, sir. Okay.
All right. Explain why the two iron complex ions are different colors. Yes, why the two iron complex ions are different colors. And FeH2O6 3 plus is yellow. So why they are of different colors?
Well, because they are in different oxidation states.
Yes,
and therefore,
due to that different oxidation states, what would happen?
well, the energy gap is different between the orbitals.
Yes, the delta
So
E
they,
between the two the orbitals, the subdivision that form, the difference of energy would be different. So they'll absorb different amount of energy, and transmittance would be different. So that's why the colors are different, right? So we can say that as the oxidation number is different, it results in different energy gap. So different frequency of light will be absorbed. So different frequency of light absorbed by both Fe2 plus and Fe3 plus. All right. Any questions?
yes, yeah.
Okay, the next part is the thiocyanate ion SCN minus forms a blood red colored complex ion with iron 2 ions. The dot and cross diagram for the thiocyanate ion can be drawn in more than one way. For example, the negative charge can be on the nitrogen atom as shown. So this is the dot and cross diagram, thiocyanate ion, in which the negative charge is on the nitrogen. Complete the alternative dot and cross diagram of the thiocyanate ion, where the negative charge is on the sulfur atom, not on the nitrogen. Use dot for nitrogen electrons. So let's first draw the nitrogen electrons. Nitrogen will share 3 of its electrons with carbon, and it would have rest 2 electrons available. So this will be the electrons. We have drawn all the electrons of nitrogen. Cross for the carbon electrons. So if nitrogen has shared 3 electrons, carbon will also share 3 of its electrons with nitrogen. So 1, 2, 3, and it has 1 left, so it will share this last carbon with sulfur. Steric for the sulfur electrons. Sulfur is sharing one electron with carbon, and it has 6 electrons, right? It has 6 electrons in its valence shell. So 1, 2, it has 4. And because we know sulfur, it will form how many bonds? 2. So 1, 2, 3, and then 4, and 5, and last 6. Right. So these are the electrons of sulfur, and triangle for the extra electron. So to complete the octet of sulfur, the extra electron would be on sulfur. So this would be the dot and cross diagram. And now we can say this extra electron with sulfur. So this is the alternative diagram where sulfur has a negative charge. Is it clear?
All right, sir. Yes.
Okay. 12.8 Cn cube of 0.05 mole per Dn cube iron 3 chloride solution reacted with 8 Cn cube of 0.08 mole per Dn cube ammonium thiocyanate to form a complex ion. Deduce the formula of the octahedral complex ion that iron 3 ion forms with the thiocyanate ion in aqueous solution. You must show your working. So we have this iron 3 ion in water. So in water, it would be FeH2O6 3 plus. This is the iron 3 ion. And we have added ammonium thiocyanate. So ammonium thiocyanate will release thiocyanate ion, SCN minus, which will act as a ligand. Right, this will act as a ligand. So a ligand substitution reaction occurs. Now we have to decide that which complex. They have told us that it would form a octahedral complex. Obviously, it would be octahedral complex. So we have to decide the formula of this complex by deciding how many water molecules will be lost, right? By solving this part. So can you do it? Just do the question. I'll have to attend a call. Okay, beta. Just do this
Okay,
question.
sir. All right.
Ji beta, have you solved this one?
Yes, I'm almost done. So I found the moles Fe3 plus and SCN, and it seems that both the moles are the same. 6.4 into 10 to the power minus 9.
6.4 into 10 to the power. Can you repeat the value, beta?
Yeah, it's 6.4 into 10 to the power minus 4.
Minus 4. Okay. And for
Yes.
thiocyanate, it's the same?
Yeah, it's the same.
All right. So that means they are reacting in a 1-to-1 ratio.
Yeah.
Right. So which means 1 mole of thiocyanate, if they react in a 1-to-1 ratio, so the formula would be Fe. How many water molecules would be lost? 5.
Yeah. 5.
SCN. And the overall charge will be changed to
2
plus
plus.
2.
Yes.
All right. Is it clear?
Yeah. Clear, sir.
So this would be plus 2. And this is what you can explain here. Okay.
Yes.
All right. How many questions are left? Okay, the next one. So we'll do inshallah I'll share this paper. You do the rest of the questions on your own. If you have any questions, like they have just one more question left, and then this organic section. So you do the rest of the question, and I think it would be easy because like you have to draw the graph, and then it's this one. Okay, I'm just in the graph question. You do it on your own. I'm just doing this part. The complex ion formed from cobalt 3 ions and ethane 1,2-diamine is a yellow-orange color. The equation for the formation of this complex is shown. Give a reason by referring to the equation. Why the formation of the diamine complex from the aqueous complex ion is thermodynamically favored. Yes, why it is by just looking at the equation. Why the aqueous complex ion is thermodynamically feasible. Why this one is more favored. Because we can see that on the reactant side, how many moles are present? 1 plus 3.
Yeah.
So it's 4 moles. And on the
Yeah,
product side, how
increase.
many moles? 1 plus 6 is equals to 7. So we can say that,
Increases.
yes, entropy increases.
Yes. Okay.
This entropy increases as more number of moles on product side. Explain by reference to the structure of ethane 1,2-diamine why it is a bidentate ligand, because it has two NH2 groups, right? Each nitrogen atom has a lone pair, and that's why it can act as a bidentate ligand. So I think it's pretty much clear. Explain how the H and H. Is this part clear, beta? Any query?
Yes,
Any
yes.
query?
No, it's clear, sir.
Okay. Explain how the H and H bond angle would be expected to change in ethane 1,2-diamine when the complex ion is formed. Yes. This is related to chemical bonding. Why the hydrogen-nitrogen-hydrogen bond angle would be expected to change in ethane 1,2-diamine when the complex is formed.
So we have to talk about the lone pairs and bond pairs and the angle, those stuff.
Yes, yes, yes. Obviously, you have to talk about the shape, the angle. So in ethane 1,2-diamine, CH2, CH2, NH2, what is the geometry of nitrogen? Like if we can look here, nitrogen is connected to two hydrogen atoms and this R group. So it has 3 bond pairs. One, it is a pyramidal geometry. Have you studied that?
Yes, yeah.
Yes, 3 plus 1, 3 bond pairs, 1 lone pair. So it's a pyramidal
Yeah.
geometry. So its bond angle would be 107.
Yes.
right? And once it bonded to once it converts into a complex, when it gets combined into cobalt. So in cobalt, what would happen? This is nitrogen. It makes a bond, and then it has two hydrogens, and then this CH2, then this nitrogen, which is connected to cobalt, hydrogen, and hydrogen. Now, if you can look here, now nitrogen is making four bonds. It has share one of its lone pair. Now the lone pair is converted into bond pair. So obviously the geometry is now changed to tetrahedral. Now it has four bond pairs. 1, 2, 3, 4. So four bond pair means 4 plus 0. This is tetrahedral geometry. So in tetrahedral geometry, the angle would be 109.5 degrees. So that's why the bond angles change. Because from three bond pairs, it is now making four bond pairs. Is it clear?
Yes, sir. Yeah.
All right. So this was the last question from this paper. This was October 2024, I think.